In this video, we're going to go through section 2.1. So in chapter 2, we're going to be talking about set theory. So in this first section, we just introduce sets and we talk about some of the language and terminology associated when we're working with a set. So in mathematical terms, if we have a collection of objects, we refer to this as a set. And the individual objects in this collection are called the elements or the members of that specific set. It's pretty typical that we're going to use capital letters to identify the set and lowercase letters to identify the elements in that set. So if we had, let's say our set is the Olympic gold medal winners, and we label that with a capital G, and then all of the elements, all of the members in that set, we identify with lowercase letters to represent the people in that set. So it's very important to choose a name for the set that's going to be beneficial and help us remember what the set is describing that we're working with. So we could choose the letter X if we're talking about, let's say, a group of Republicans. And we could choose Y if we're talking about a group of Democrats. But it might be a little bit easier for us to use letters that make more sense if we identify Republicans as the set R and Democrats as the set D. So when we're talking about representing a set, we usually do this by listing each element in braces. So if we're looking at the seasons of the year, that set could be the set S. And so we notice here, if we represent that set, we have our curly braces, and then we're just listing all 4 seasons within those curly braces. There are times where it's possible to list every element of a particular set. Other times it might be more inconvenient for us to do that. For example, if we were to think about all of the numbers, all the natural numbers between 1 and 1,000. So if we wanted to do that, rather than listing all of those numbers between 1 and 1,000, we could list a few, and then we could do our 3 dots, our ellipsis, and then we could list the last number in that set. And so that ellipsis indicates for us that the list continues in that same pattern or in that same manner up to the last number in the set. So we could also write this set of whole numbers in a similar manner. If we don't have a stopping point, because the whole numbers never end, we could just list out 1, 2, 3 and put the ellipsis, and then we don't have a number following it, so that means that particular list does not end, as we can see right here. It just keeps going on forever and ever. If we have our elements and they all share some common characteristic, then we can use what we call set builder notation to represent this set. So if we have our set C, and that is all of our carnivorous, all of our meat-eating animals, then we could use our set builder notation to set it up. So when we look at the way this is set up right here, we have a breakdown right here. So C is representing our set. We have equals, or we could also read that as is, and then we have our curly brace. And so that tells us we're starting our set. We have our variable, so of all X is saying everything of that type. Our colon, we read that as such that. And then we state what the condition is. What are we describing in that set? And in this case, X is a carnivorous animal. So C is the set of all X such that X is a carnivorous animal, is how we would read that. Okay, and so they give a couple of examples. A lion would be an element, would be a member of that group, but a lamb would not be. So we're going to spend some time starting off just looking at how we can describe different sets of numbers. So the first set we have is called the natural numbers. And so another way to refer to this, and you'll see that as you're going through the homework, the natural numbers are also referred to as the counting numbers. So we have our natural numbers or our counting numbers. So we use a capital N to represent the natural numbers. We have our equal sign. So the set of natural numbers is the set. And then we're just going to list out some of them. Now, we won't be able to list every single counting number, but if we think about counting objects in a room or counting people in a room, we know that we're always going to start with 1. So we have 1, 2, 3, 4, 5, 6, and there's no ending point. So we could continue to list numbers. We could also put our ellipsis and then just close our curly brace. And that tells us that from the time we start counting, there's not a definite ending point because it could continue on. Part B is the whole numbers. So the whole numbers are the counting numbers. The only difference is when we're talking about whole numbers, we add one extra number to our counting numbers. So we have the counting numbers and 0. So our whole numbers we represent with a capital W equals the set, and then we start listing at 0, and then 1, 2, 3, and so on. The next set we have are the integers. So with our integers, when we're listing those, this book uses a capital I. And our integers are the whole numbers and negative values. So it's not just, we notice that the last two are counting our natural numbers. We're just those positive whole numbers, 1, 2, 3, and so on. The counting numbers, not the counting numbers, the whole numbers, our second set, added 0 to that list of counting numbers. With the integers, we're expanding that scope even more, and we're focused on positive and negative. So extending in both directions, our set starts where there's no ending point if we think about those negative values. And then we could list -3, -2, -1, 0, 1, 2, 3, and we could keep listing because with the integers, it goes on in both the positive and the negative direction. Next, we have our rational numbers. When we're talking about rational numbers, those are numbers that can be written as a quotient. And because of that, when we describe the rational numbers, the letter we use to represent that set is a capital Q because it's representing quotients. Now, we're not going to list out values here like we've done with the last few because there is a very specific condition and criteria that has to be met. So what we're going to do is we're going to have our curly brace. We're going to have our set represented as X. We're going to have our colons such that, and then we're going to write what is the condition that X has to meet to be included in this set. So when we're looking at this, if we have a quotient, then we want the numbers in this set, our values for X, to be able to be written, so X can be written in the form A divided by B. So that form is our quotient. And we do want to specify there are restrictions on A and B. So in this form, A and B are both integers. So they're both those positive or negative whole numbers. And the other condition is because we have a quotient, because we have division. B cannot be 0 because we can't divide by 0. And then the last set we have when we're talking about numbers are called the real numbers. So the real numbers are similar to our rational numbers. The only difference is if we think about our real numbers, we use that capital R, but it's going to be the set of x values, the set of values such that x has a decimal expansion. So this is saying any value that we can write as a decimal or with a decimal expansion is going to be a part of this set. So our next example gives us some sets, and it wants us to use a different format to just rewrite the given set. So with part A, we have set T. And so looking at this set, we notice that all of these are different blood types. So another way we could write this set using the same letter to represent the set, but rather than listing out all of those types, we can just indicate what our condition is. So this would be the set of x values such that x is a blood type. So again, just indicating what are the conditions. Now with part B, they give us our set and they actually give us what the conditions are. So in example B, our set is the set of y values, so using a different variable there, such that y is a color of the American flag. So if we want to write this in a different way, we're still going to have the same set. But this time, rather than stating the condition, we can just list all of the colors that meet this criteria. So we would have our set, and then we would just list out the colors of the American flag. So that would be red, white, and blue. Part C gives us our set, and it's the set of A such that A is a counting number less than 20 and evenly divisible by 3. So we have a few conditions here. Counting number, less than 20, evenly divisible by 3. So first, when we're thinking about our set A, we want to think about what are the counting numbers. So if we refer back to what we did earlier, our counting numbers are those natural numbers when we started at 1. So we had 1, 2, 3, 4, 5, and we could keep going. So we're thinking about that group of numbers where they're also less than 20 and that last condition evenly divisible by 3. So that means whatever numbers we pick are going to be divisible by 3. Can be divided by 3. So if we think about the numbers that can be divided by 3, we said those counting numbers. So 1, 2, 3 is the first one. 4, 5, 6 is the next one. Then we have 9, 12, 15, 18, and the next number that we could divide by 3 would be 21. However, we're looking at numbers that are less than 20, so that means we have found the last number in this set that meets all of those criteria. So the next thing we talk about is, and I'll leave the quiz yourselves for y'all to try, but the next thing we talk about is a set. So a set, building on the idea of a set, we can have a set that is well-defined or not well-defined. And what we mean when we're talking about a set that's well-defined is if we're able to tell whether any particular object is an element, is a member of that set or not. So, if we look at our first example with part A, the set is telling us that it's the set of X values such that X is a winner of an Academy Award. So when we think about, is this set well defined or not, we want to think about, is it very easy to determine if somebody would be an Academy Award winner or not? And so if we put it in that perspective, we would be able to say, yes, the set is well defined. Because you can very clearly think of any celebrity that you want, and either they are an Academy Award winner or they're not. So it's very easy to say definitively, without a shadow of a doubt, yes or no to this. So you can easily determine if someone is an Academy Award winner or not. The next example we have for part B says the set T is the set of X such that X is tall. Well, again, if we think about, being well defined and you being able to very concretely, very definitely say yes or no, like we did with the last one. Yes, this person is an Academy Award winner. No, that person is not. In this case, this set is not going to be well defined. And the reason being, if we were to have a conversation about if I am tall or not, some of you may say I am tall. Some of you may say I'm not tall. So that's what we want to think about when we are discussing, is the set well defined? In this case, it's not cut and dry. Everyone has their own opinion, their own perspective. So you can't say without a shadow of a doubt yes or no, because everyone's interpretation of being tall is going to be a little bit different. So being considered tall is a matter of opinion. Okay, so that's our difference with being well-defined versus not well-defined. Okay. So again, a couple of try yourself problems. I encourage you to just take a couple of minutes, see if you can put those in the appropriate category. Now, when we are using set builder notation, we do have the possibility that there's a condition that's been established and there's nothing that satisfies that particular condition. So the example they give is if our set is M and the elements in that set are your math class and also plays in the National Football League. There's nothing that's going to satisfy both of those criteria, so that has no members, no elements. If we have a set that has no elements, we call that either the empty set or the null set. And there are a couple of different notations you'll see for that set. You could see this symbol. It kind of looks like an O or a circle with a diagonal line drawn through it. And then you also have just the curly braces without anything in between them. Okay. And so again, like we said, in this case, that set that we were just discussing about your math class and playing in the NFL is the empty set. So we would write that in this notation. Now, with the empty set and with this notation, we do have to be careful sometimes based on the way things are presented. So, with this example right here, we have, does the set containing the empty set have the same meaning as simply the empty set? So, to think about this, one way that we can kind of approach it would be to think of a set as a paper bag that you would get when you're checking out from Kroger or Market Basket or wherever you do your shopping. So if we think of a set as a grocery bag, and we think of the empty set as an empty bag, but if we think of this set right here, that is saying that we have a bag, a plastic bag, with another empty bag inside of it. So these two are not representing the same thing. They do not have the same meaning. Part B says, what about if you have the set containing the empty set and the set containing 0? Well, if we go back to that idea of thinking about the grocery bag, we said if we have the set with the empty set, then that means you have a plastic bag and you have another bag inside of that one that doesn't have anything in it. Whereas this notation is saying that you just have one bag that doesn't have any groceries in it. So again, these are not representing the same thing. So we can have a set that doesn't have any elements in it. We said that's the empty set. But we also have what's called the universal set. And so this universal set is the set of all elements under consideration given a particular discussion. And the universal set is very often represented with a capital U. So let's say that we are working a problem where we're only focused on the counting numbers from 1 to 10. In that conversation, in that scenario, the universal set is the set that contains all of those counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, we could also think about if our focus is kind of on female consumers living in the United States, then the universal set would be the set of X, where X is a female consumer living in the United States, because it's everything in that particular set. When we are looking at using mathematical notation to indicate if something is an element or a member of a set, we have a symbol that looks like an E. And so that represents the phrase is an element of. And so while it does look like the letter E, they are not the same and should not be confused as such. Okay. This notation, so 3 with our element symbol of A, is telling us 3 is an element of the set A. If 3 is not an element of that set, then we draw that same symbol and just draw a diagonal line through it. So with example 5, we are going to look at filling in the blank. So we're just filling in the blank. We don't have any pound symbols to replace here, like you might see in the homework, but we're just going to fill in the blank with either the element symbol or not element symbol to make the statement true. So with part A, we have 3, and then we have our set, And inside that set, we have 2, 3, 4, and 5. And so we notice because 3 is inside that set, 3 is an element or a member of that set. Now we do want to be careful because part B looks very similar to that, but this time we notice it's the set with 5, and then the second set has 2, 3, 4, and 5. So because the set containing just 5 is not in this second set of brackets, this is not an element. Example C says Elon Musk, and then our set is X is a billionaire. Well, Elon Musk is a billionaire, so he would fall in that category. Part D, jogging, and then our set is that we're looking at aerobic exercises. So again, jogging is an aerobic exercise, so it's an element of that set. And the last example we have, before y'all get into the try these, is the Ace of Hearts, and then we're looking at our set being face cards in a standard 52 deck. So an Ace of Hearts is a card, but it's not a face card. So that means this is not an element of that set. And then we have a few examples right there for y'all to try. The next thing we talk about is cardinal numbers. So when we're looking at set theory problems, a lot of times we need to know the number of elements in a set. And the number of elements in a particular set is what we refer to as the cardinal number of that particular set. And our notation is a lowercase n, and so that makes us think of the word number. And then in parentheses, we have our capital letter that is connected to the set we're focused on. Now, when we're thinking about cardinal numbers and we're thinking about sets, a set can fall in one of two categories. It can be finite, so meaning the elements are countable. So that means the cardinal number is a whole number. If it's finite, we can count it. We can get a whole number for the number of elements. We could also have a set that is infinite, meaning it's not finite. So if it's infinite, that means we can't count it because it just continues on forever and ever and has no clear stopping point. So with our next examples, we want to state whether each set is finite or infinite, and then we have another condition that says if it's finite, state the cardinal number using our notation. So state whether it is finite or infinite. So example A gives us the set P. And so in this set, X is a planet in our solar system. So if we think about this and we think about, is that something that's finite? Is that something that's countable? Yes. If we think about the planets, there are 8 planets in the solar system. So because it is countable, it's finite, we can state the cardinal number using our notation. So we have the number, and then in this case, our set is P. So we have the number of elements in P equals 8 because we have 8 planets. Part B, we have the set of counting numbers or the set of natural numbers. And so if we think about the set of counting numbers, if we start counting 1, 2, 3, 4, we could just keep counting for as long as we wanted and we would never have to stop. So the set of counting numbers is infinite. Remember we said these are the counting numbers or the natural numbers are the two different ways you'll see them referred to in the text. Part C gives us the set, and it says our set A is where Y is a person living in the United States who is not a citizen. With this one, we did have two conditions. First, to figure out if that's something we can count or not. This situation, if we wanted to know the number of people living in the US who are not citizens, that is a finite countable number, but it's very likely that none of us are going to know what that number is. So this one is finite, but we don't know what that number is, so we're not going to be able to write it using that cardinal notation. So we said this set is finite, so there is some cardinal number. However, we don't know what it is. We do not know how many people living in the US are not citizens. Part D is the empty set, and we said the empty set has no elements. And so because it has no elements, it is considered finite. Because if you have nothing, then you have 0. So the cardinal number of the empty set is just 0. Okay, and then the last example we have right here before y'all have a few to try on your own is the set X. And the set X is a set that has 3 sets inside of it. So we can think of each of these sets as their own object. So the set X contains 3 objects. So our cardinal number for this set is going to be 3. So there are a couple of examples for y'all to try. And then one of the last things we look at in this section is just getting some more practice with kind of identifying if a set is finite or if that set is infinite. And so we have a couple of examples there before we look at example 8. So the first example in number 7 says our set is the set of Y, such that Y is the amount of people who have walked on the moon. So if we're trying to think about if that's countable or not, could we count how many people have actually walked on the moon? Because walking on the moon is not a very common thing, this would be something that we would be able to count. So this set is finite. Part B is the set of X, such that X is an element of the empty set. Well, as we were kind of just discussing, the empty set has no elements in it. So because it doesn't have anything in it, it contains 0 things. So that is something that is finite. Because it has 0 elements in that set. So the last example we have in this section is a couple of situations where we have 2 sets and we're trying to figure out if the first one has an element that is in the second one or not. So we're trying to see if there is a relationship here. So the directions say find an element of the first set that's not an element of the second set. And it does tell us there are many correct answers. So the answers that I have going through these are not the only answers, and you probably could easily come up with other answers. So we are looking at set A, and we're thinking about what are the criteria or the conditions in that set. And then we're looking at set B, and we're trying to find something that matches the criteria from set A, but does not satisfy the criteria for set B. So with our first example, set A is the set of Y such that Y is a member of the human race. B is the set of Y such that Y is a citizen of the United States. So if we're trying to find something that's in the first group but not in the second group, then we're trying to think of an individual who is a human but is not a citizen of the United States. And as we said, there are a lot of different answers to this problem. The one that I'm going with is the Queen of England. Queen of England is a member of the human race, but is not a citizen of the United States. Part B, the first set is the set of Y such that Y is an animal. And the second set is the set of Y such that Y is covered with fur. Again, lots of options here because the first set is just an animal. So there are lots of different animals out there. We're looking for one that is not an animal covered in fur. So an example of that would be a frog. Part C. The first set is the set Y, that Y is a car manufacturer. And then our second set is that it is a company based in the United States. So we need a car manufacturer, and then we need one that's not based in the United States. So we could say Kia. And then the last example we have in this section is looking at the first set is the set of Y, where Y is a state whose name begins with the letter A, B, or C. The second set is the set of Y, where Y is a state whose name begins with the letter A or B. So we need a state whose name begins with A, B, or C in the first set. And then we need one whose name does not start with A or B in our second set. So again, we have a few options here. I'm going with California. California is a state whose name starts with C, and then since it starts with C, it does not start with A or B, so it falls in the first set, but not in the second set. So that is just a little introduction to set theory. We're going to continue to work with sets more as we progress throughout this section.